Hello everyone. In this video, we're going to learn how to solve quadratic equations by completing the square. In the last video where we covered the square root property, we mentioned that the square root property will eventually help us solve all quadratic equations, even the ones that are not very simple, like the type we encountered in the last video. And today we'll get into how we're going to do that using the method called completing the square. Before we actually get into the method of completing the square, let's consider a simple expression like the square of this binomial, x plus 3 squared. As you know, we can write that as x plus 3 times x plus 3, and of course multiply it out and end up with x squared plus 6x plus 9. Now, a very useful thing for us would be to be able to take an expression like x squared plus 6x and ask ourselves, what number do I need to add to x squared plus 6x so that it does turn into a perfect square of a binomial such as x plus 3 squared? And of course, in this simple case, we know it's 9 because we saw it worked out here. But what if you had another expression like x squared plus 10x? What we want to know, is there enough information hidden inside x squared plus 10x itself that will help us find that number that's missing, such as in the previous case it was 9? What would it have to be so that when we add it to x squared plus 10x, it also becomes a perfect square trinomial? As you know, a trinomial such as x squared plus 6x plus 9, which can be written as the square of a binomial, is called a perfect square trinomial. So that's the goal, to take just the square term and the x term and find out the number we need to add to it to make it a perfect square trinomial. And regarding the question of is there enough information hidden in just those two terms, it turns out that if the coefficient of the x squared term, which we call the lead coefficient because it's the coefficient of the highest degree term in a quadratic expression like that, is 1, then the answer is a resounding yes. To see why that's true, let's take this and look at a more general form of it, such as x plus just some unknown number n squared. If we multiply it out like we did up here, we'll end up with x squared plus 2nx plus n squared. Now, if we look carefully, we'll see that there is a nice relationship between 2n and n squared. It turns out if you take half of 2n, you end up with n, and then of course if you square that, you'll get the n squared that is required to turn x squared plus 2nx into a perfect square trinomial. So that is the method we're going to use on an expression like this as well. So we'll take a look at some examples and explore that in the next screen. But make sure you understand these basics before we proceed. First of all, make sure you understand that it's extremely important to notice the fact that this process we're about to use, which entails taking half of the coefficient of the x term, or the first degree term as it's called, and then squaring it to get the number that's missing to make this expression into a perfect square trinomial, will only work if the coefficient of the x squared term is 1, as we just mentioned. So that's super important to remember. But once you do remember that, then the process of completing the square here is quite simple. It's a two-step process. In the first step, we take 1/2 the coefficient of the x term, which is 10 here. So we take 1/2 of 10. That gives us 5. And then in the second step, we take 5 and square it to get 25. That's exactly the number that we need to add to x squared plus 10x in order to turn it into a perfect square trinomial, which, as we know from this rule, that f squared plus 2fl plus L squared equals quantity f plus L squared. We know that this is going to be x plus 5 squared. The nice thing is that the number that's going to go in here is going to be the number we obtained in the first step. So that makes it easy to write this expression as the square of a binomial. So it's a very simple process, but as you'll see in a minute, it's very important and very, very useful. Okay, let's go ahead and take a look at another problem. So here we have y squared minus 7y, and we're going to go through the same kind of process. So the first thing we're going to do is to take 1/2 of the coefficient of the first degree term, which will be -7, and we end up with -7/2. Now for the second step, we're going to take the -7/2 and we're going to square it to get 49/4. So now we know that this is the number we need to add to y squared minus 7y in order to turn it into a perfect square trinomial. So now we write y squared minus 7y plus 49/4, and we go ahead and write it as the square of a binomial. And remember that the result of the first step is what's going to go next to y in this case. And so we're going to have y minus 7/2 squared. Of course, you can verify that quickly, and by realizing that when you take y minus 7/2 and square it, you can use the rule that says f minus L squared equals f squared minus 2fL plus L squared to get, of course, here f will be y and L will be 7/2. So we end up with f squared, which is going to be y squared minus 2 times f, which is y, times 7/2, which is L, plus L squared, which is 7/2 squared. And we end up with y squared, the 2's here will cancel out, minus 7y plus 49/4. So there we have verified that it is indeed become a perfect square trinomial, and it's the perfect square of this binomial. Understanding this process is going to be very important for us. So make sure you can handle this kind of a problem before you proceed. Okay, so here we have another example, this time with the variable t. Definitely try to do this on your own before you watch the rest of the video. Welcome back. So we know that we take 1/2 of 3/5, which ends up giving us 3/10. And in the next step, we're going to take that 3/10 that we obtained in the first step and square it to get 9/100. So we're going to take t squared plus 3/5 t, and we're going to add 9/100 to it, and now we know that is going to be a perfect square of the expression t plus 3/10, and that's how you complete the square on a partial quadratic. Okay, now we're ready to go ahead and proceed with solving quadratic equations by completing the square. And basically, it's important to understand this method is extremely powerful, what we're about to explore. And it is a universal method in the sense that it won't just solve some special kinds of equations, quadratic equations like the ones we have seen, such as the ones that can quickly be solved using the square root property, or the ones where we can get all the variable terms and together with the constant on one side, 0 on the other side, and then proceed with factoring and using the zero factor property. No, this method will solve any quadratic equation, even the ones with complex solutions or any other kind of situation, such as the one with fractional exponents, and not exponents. Now we're ready to go ahead and proceed with solving quadratic equations by the method of completing the square. This is an extremely important method in the sense that it is universal, meaning that it will solve any quadratic equation that can be put into this form: ax squared plus bx plus c equals 0 with real coefficients. Of course, you don't want a to be 0, because if it is, it just becomes a linear equation. So that's the only restriction we put on it. Some of the methods we've already learned, such as the square root property or solving quadratic equations by factoring, they're only useful with very special kinds of quadratic equations. This method, which we'll discover in a minute, will be able to solve any quadratic equation. So here we'll outline the procedure using an example, which is the best way to understand it. Let's say we want to solve the equation x squared plus 10x minus 24 equals 0 using the method of completing the square. So the procedure is actually quite straightforward. You go ahead and take the x squared term and the x term and put it on one side of the equation and move the constant to the other side. If there is some simplifying that can be done first, you do so, combining like terms. Sometimes you may not exactly be in this form. You may have the 10x or the negative 24 on the other side, etc. But after all the simplifying, basically you want to get to this place where you have the x squared and the x term, meaning the second degree and the first degree terms on one side, and the constant or the 0 degree term on the other side. Now, at this point, if the coefficient of the x squared term is not 1, we go ahead and divide both sides by it, because remember, the method of completing the square depends on this coefficient being 1. In this case, it's 1, so we can proceed. The next thing you do is you go ahead and complete the square on the first two terms on the left side here, just like we did in the previous few examples. So we take 1/2 the coefficient of x, which is 10, that gives us 5, and we go ahead and square that to get 25. Now keep in mind, when we were completing the square before, we were just working with expressions. Now we're dealing with an equation. That means if we're going to add this 25 to the x squared plus 10x, we have to do the same on the other side, because we always have to do the same thing to two sides of an equation. So now we end up with x squared plus 10x plus 25 equals 24 plus 25. Now, if we simplify, we just end up with this. So at this point, we're going to go ahead and write this perfect trinomial, square trinomial that we obtained in the form of the square of a binomial like this. And now you can see where the square root property ties into all this, because this is exactly the kind of equation we solved in the video that we called the square root property. So we know that if the square root property states that if x squared equals k, then x equals plus or minus square root of k. We also had the more general version, which said if you have, instead of x squared, you have ax plus b squared equals k, then you can make the same conclusion, but this time you'll have to say ax plus b equals plus or minus square root of k. So here we're using this more general version, so we get x plus 5 equals plus or minus square root of 49. Of course, we know that the square root of 49 is 7, so we just get x plus 5 equals plus or minus 7. And that gives us, moving the 5 to the other side or subtracting 5 from both sides, we get x equals negative 5 plus or minus 7. Of course, with these, we know that when both of those numbers end up being integers, we should go ahead and do the plus case and the minus case and get two actual integral solutions. So here, when the plus case gives us negative 5 plus 7, which gives us 2. And the minus case gives us x equals negative 5 minus 7, which is negative 12. And we end up with this solution set. Of course, when this happens, this tells you that this problem could have been solved by factoring, but we wanted to demonstrate the method of completing the square here. Usually when these end up being irrational or complex, then that's when the method of completing the square would have been absolutely necessary. Of course, if we take a look at this, x squared plus 10x minus 24 equals 0, we know that we can factor this as x plus 12 times x minus 2 equals 0, and then apply the zero factor property to give us either x plus 12 equals 0 or x minus 2 equals 0. So we end up with x equals negative 12 or x equals 2, which is of course the same two solutions. But most of the problems we're going to be encountering are not going to be of this simple factorable variety, as you will see in a minute. So make sure that you understand the procedure. Again, simplify and move the x squared and the x term to one side, the second degree and first degree terms to one side, and the constant to the other side. Doesn't matter which side you choose. Usually we go to the side which keeps the x squared positive for simplicity. Then we find the constant that you need to complete the square on the variable side, because remember the other side is constant. So on this side, of course, we know that we have to take half the coefficient of the x term and square. And once you do, you go ahead and add the constant to both sides. We write the equation in a square of a binomial form, and we apply the square root property. Then we write our solution set. So we'll do that next with another problem. Okay, let's go ahead and take a look at this problem now. So of course we're going to try to simplify and then separate the y squared and the y term from the constant. There's not much to simplify on either side. In fact, there is no simplification possible, so we'll go ahead and put the y squared and 4y on the same side, so we get y squared plus 4y. Because when we change sides, we change signs, and we put the negative 11 on the other side to become 11, of course by adding 11 to both sides. Now we're going to determine the constant we need to add to y squared plus 4y to turn it into a perfect square trinomial. That's usually, as I said, side work, so we'll go ahead and do that on the side here. So we know that we need to take 1/2 of 4, which is 2, and we need to go ahead and square that to get 4. So now we're going to go ahead and add 4 to both sides of this equation. Anything we do to one side, we have to do to the other side as well. So now when we simplify that, we get y squared plus 4y plus 4 equals 15. So now we will take this perfect square trinomial that we've created, and using the fact that f squared plus 2fl plus l squared equals quantity f plus l squared, go ahead and rewrite it as the square of y plus 2. And remember that the first step of the completing the square process always gives us the constant that's going to go in here. So y plus 2 squared equals 15. Now that's ready for the application of the square root property. So therefore, by the square root property, we get y plus 2 equals plus or minus square root of 15. Now we can go ahead and just solve that for y. So we end up with y equals negative 2 plus or minus square root of 15. And of course, this is representing two solutions. We realize that one of them is y equals negative 2 minus square root of 15, and the other one is y equals negative 2 plus square root of 15. So when we write our solution set, we'll go ahead and break them up as two solutions: negative 2 minus radical 15, comma, negative 2 plus radical 15. And we used to actually let students just leave it like that, except a lot of students didn't realize these are actually two solutions. So now we prefer that you split them up like this so that it's completely clear that we're dealing with two solutions here. So make sure that you can handle that on your own before we proceed. Okay, so we have another problem here. You should definitely try on your own before you rejoin the video. All right, so we can see here that we need to go ahead and get u squared and 3u on the same side. So we get u squared plus 3u. And on that side, 40 is already sitting, so we just leave it where it is. Now we go ahead and find what we need to add to complete the square. Remember, this is normally side work. We don't want to write it in the flow of our problem. So we'll take 1/2 of 3. This will be kind of our CTS corner here, completing the square. That gives us 3/2. Then we take the 3/2 and square it to get 9/4. So we know that we need to add that to both sides. So we get u squared plus 3u equals 40. And we're going to go ahead and bring in plus 9/4 on both sides. So basically, if we go ahead and do a little bit of algebra here, we get u squared plus 3u plus 9/4 equals, here we're going to have to get a common denominator. Don't forget there's a 1 under the 40. So we can see that we're going to have to multiply this 1 by 4. So we'll do the same on the top. So 4 times 4, 40 is 160 plus 9 will give us 169/4. So now we're going to go ahead and write this perfect trinomial squared. Actually, let's try it again. Perfect square trinomial, and rewrite it as the square of a binomial. And of course, that's going to be u plus whatever we got in step 1, always 3/2 squared equals 169/4. Now we're ready to go ahead and apply the square root property, and we end up with u plus 2 having to be either positive or negative square root of 169/4. So we get u equals negative 3/2 plus or minus, we're subtracting 3/2 from both sides. Now we know the square root of 169 is 13 and the square root of 4 is 2. So we can just write 13/2. These are both rational numbers. We should go ahead and combine them. So the minus case and the plus case, well, let's see. The minus case will give us u equals negative 3/2 minus 13/2. And the plus case will give us u equals negative 3/2 plus 13/2. Back to the minus case, we get negative 16/2, so it's negative 8. And on the right, we have negative 3 plus 13, which is 10/2, which gives us u equals 5. So now we can write our solution set, which contains negative 8 and 5. Just wanted to show you how to handle it. If fractions appear, just don't panic. It's the same as the one with whole numbers or integers. You know how to handle fractions, so that's all there is to it. No different from having just regular integers. All right, so make sure that you can handle it, however, and we're going to move to another problem. All right, so for this next one, we notice that as far as simplifying goes, both sides are simple, but we do notice that, remember, one of the requirements is if the coefficient of the square term is not 1, you have to divide by it, because remember, the process of completing the squares depends on the coefficient of x squared being 1. So we go ahead and write the problem, 8x squared plus 8x equals 32. And now we'll go ahead and divide both sides by 8. Of course, this will split up, so we get 8x squared over 8 plus 8x over 8 equals 32 over 8. So simply x squared plus x equals 4. Notice there is no reason to factor out the 8. Rather, just this process here is called dividing it off, because this can be done with equations and it literally comes off the equation. That's why we call this process dividing 8 off the equation. And now we end up with this simpler format here. So now we go ahead and proceed by finding the constant we need to add to complete the square on this. Of course, the coefficient of x being 1. So we have 1/2 of 1. This is our CTS corner here. That gives us 1/2. And we're going to take the 1/2 and square it to get 1/4. So we go ahead and add 1/4 to both sides, and we end up with x squared plus x plus 1/4 equals 4 plus 1/4. Now, that gives us x squared plus x plus 1/4. Here, of course, we're going to have to get a common denominator of 4, which means we need to multiply the 1 by 4 and the same with 4. So we end up with 16 plus 1, which is 17 over 4. Now we rewrite this as the perfect square of a binomial. And of course, we know that's going to be x plus 1/2 here squared. Another way of figuring it out is what do you have to square to get that, but then you have to watch this sign too. But if you look here, the sign will already be figured out for you too. We knew it's going to be positive. So we end up with equals 17 over 4. Now we apply the square root property, and we end up with x plus 1/2 equals plus or minus square root of 17 over 4. So x equals negative 1/2 plus or minus square root of 17. And of course, we know the square root of 4 is 2. So one way we can write the solution set is to say negative 1/2 minus square root of 17 over 2 comma negative 1/2 plus square root of 17 over 2. Or sometimes in some textbooks you may see it as combined, like in this manner. So negative 1 plus square root of 17 over 2 and negative 1 minus square root of 17 over 2. Both are acceptable forms of this solution set. And that's how we handle the situation where the lead coefficient is not 1. We basically just divide both sides by it and then proceed as normal. Make sure you can handle this as we go to the next problem. Here we'll look at a problem that will end up giving us some complex solutions, but the approach will be exactly the same. We'll go ahead and get x squared and negative 2x on the same side, which will turn into plus 2x, and we'll get the 4 on the other side where it will become negative 4. So now we'll go ahead and complete the square. So we need to find 1/2 of 2, which is 1, and we're going to take the 1 and square it to get 1. So we need to add 1 to both sides of this equation. So we'll end up with this scenario, and then we'll simplify to get x squared plus 2x plus 1 equals negative 3. Now we'll go ahead and write x squared plus 2x plus 1 as the square of a binomial, and we know that's going to be x plus 1 squared equals negative 3. I'm not necessarily going on the quite same portion as this. I'm just reproducing these to remind you of the steps. And now we're going to go ahead and apply the square root property, which gives us x plus 1 equals plus or minus square root of -3. So we get x equals -1 plus or minus, and we'll go ahead and break that up into square root of 3 times square root of -1. So we get x equals -1 plus or minus square root of 3. We always want to replace square root of -1s with I. So you can see we have two solutions. One is -1 minus square root of 3i, and the other one is -1 plus square root of 3i. And these are complex conjugate solutions. And again, in some textbooks, you may find this written as -1 plus or minus square root of 3i. In fact, especially if you're looking at an older textbook, you'll see that. So it's basically the same thing written in compact form. And again, these are called complex conjugate solutions. And that's how you handle that. It's no different from any of the other ones we have done. Let's go ahead and take a look at this problem, which looks slightly different from the others. I would definitely recommend that you try it on your own first. Okay, I'm assuming you did. Welcome back. Notice that here we do have a little bit of simplifying we need to take care of. So we're going to go ahead and distribute the 3x here. We'll get 3x squared plus 6x equals -5. Also, the lead coefficient is not 1, so we're going to go ahead and divide both sides by that lead coefficient, which is 3. And of course, on the left side, it splits up like that, and we end up with this situation. So we end up with x squared plus 2x is equal to -5/3. Now we're going to go ahead to our CTS corner here and find out what we need to add to x squared plus 2x. To make it a perfect square trinomial, we take 1/2 of 2, which gives us 1, and then we take the 1 and square it to get 1. So we need to add 1 to both sides. So we get equals -5/3 plus 1, which we can of course write as 3/3 to help us save one step. All right, so on the left side, we know we have x plus 1 squared. On the right side, we have -5 plus 3, which is -2/3. So now we go ahead and apply the square root property to get x plus 1 equals plus or minus square root of -2/3. So we get x equals -1 plus or minus. Let's go ahead and break that up as square root of 2 over square root of 3, and we'll get a square root of -1 on the top as well. So we get x equals -1 plus or minus square root of 2 over square root of 3i, and we need to rationalize that denominator, so we're going to go ahead and multiply by square root of 3. So we get x equals -1 plus or minus square root of 6 over 3i. As far as standard complex form is concerned, this is perfect. So we can go ahead, let me go over here and write it. So we get s equals -1 minus square root of 6 over 3i, comma, -1 plus square root of 6 over 3i. All right, that said, you may not find that answer in many different contexts, and you may see the solution written in this way. A lot of times people go ahead and combine these fractions by getting a common denominator, and they write the solution set in this way. They write the solution set equals, so if you go ahead and combine those, you're going to need a denominator of 1, which then you'll multiply by 3, and you'll do the same to the -1. So you get -3 minus square root of 6i over 3, comma, and the same on the right side, -3 plus square root of 6i over 3. All right, so if the problem mandates that you write the solutions in standard a plus bi complex form, you'll definitely want to leave it like this, which is, again, from a mathematical standpoint, the preferred form. But if it doesn't, it'll accept this solution as well. They're both correct. And that's that. So make sure you can carry on one like this completely on your own without having to look at all, and then we'll go to the last problem that we're going to look at next. Okay, so we're finally ready to look at the last problem we're going to handle tonight, and it's actually one for the road. You're going to be doing it. I'm just going to make sure that you know how to handle a situation like this with fractions. The good news, of course, is that given that this is an equation and we know the multiplication property of equality, which means you can multiply both sides by the same number, we can go ahead and clear the fractions. So we find the LCD, which is 12, and we go ahead and multiply both sides of this equation by 12, and which means we have to distribute the 12 on the left side. So we end up with 12 times 1/2 x squared plus 12 times 1/3 x plus 12 times 1/4 equals 12 times 0. So we have some cross canceling here. So we see that 2 and 12 leave us 6 on the top, 3 and 12 leave us 4 on the top, 4 and 12 leave us 3 on the top. So the simplified fraction, or equation rather, becomes 6x squared plus 4x plus 3 equals 0, which is just a regular equation like all the other ones we've handled tonight. So you should be able to handle this. When you do, make sure you end up with this solution set with these two complex conjugate solutions. And that should pretty much do it for tonight. You should be able to handle solving quadratic equations by the method of completing the square at this point with no problem. So be safe until the next time that we meet.